Well, let me tell you about something that seems very simple but turns out to be one of the strangest things in all of physics. You take a piece of glass, ordinary glass, and you shine light at it. Some of the light goes through, some of it bounces back. About 96% goes through, 4% reflects. That seems reasonable, right? Glass is transparent. Most light should go through. But now you do something very simple. You make the glass a little thicker. Not much, just a tiny bit thicker, and you measure the reflection again, and here is what you find. The reflection drops to zero, zero. No light reflects at all. Make it a bit thicker still, and suddenly 8% reflects. Make it thicker again, and you are back to zero. Then 4%, then 8%, then 8%, then zero. Think about that for a moment. The amount of light that bounces back depends on how thick the glass is. But here's the problem. According to everything you learned in school about light, this makes no sense whatsoever. A photon hits the front surface of the glass. It either bounces back or it does not. What could the thickness of the glass possibly have to do with it? The photon has already made its decision at the front surface. It does not know how thick the glass is behind that surface. You see, this is not some tiny experimental error. This is not imperfections in the glass. You can make the glass absolutely perfect, and this still happens. The pattern is completely regular. 048404840. Over and over, as regular as a heartbeat. Now, physicists spent decades trying to explain this, and every obvious explanation fails. You might think, well, maybe some photons are different from other photons. Maybe some are the bouncing kind and some are the going through kind. But that does not work, because if you change the thickness of the glass, you change which photons bounce. The same light source, the same photons, but different thickness means different reflection. So the photons themselves cannot be carrying the information about whether they will bounce or not. You might think maybe it is about imperfections in the glass surface. Maybe when the glass is exactly the right thickness, the imperfections line up in some way that stops reflection. But no, no, no. You can make the glass surface absolutely perfect, polish it to atomic smoothness, and this still happens. The pattern does not change. Classical physics, the physics of Newton and Maxwell, has no explanation for this. None at all. You can write down all the equations for how light should behave as waves or particles, and none of them predict this thickness dependence. This is a genuine mystery, and the solution to this mystery is quantum electrodynamics. Let me tell you what happened. In the 1940s, there was a group of physicists working on this problem. Richard Feynman was one of them. Julian Schwinger was another. A Japanese physicist named Ichiro Tomonaga was working on the same thing independently. And what they figured out, what they discovered, was something so strange that even now, even after all these years, it is hard to believe it is true. Here is what they said. A photon does not just reflect off the front surface or the back surface, it reflects off every point in the glass, every atom, every possible location. And not just that, the photon takes every possible path. It goes straight through. It bounces off atoms at crazy angles. It curves through space. It even, in some sense, goes backward in time. Every path you can imagine, the photon takes it. Now, you might think this is just poetry, just a way of talking about the math. But no, this is how you actually calculate what happens. You represent each path with what Feynman called a little arrow, a probability amplitude. The arrow has a length and a direction. And here is the beautiful part. For each path the photon might take, you draw an arrow. Then you add up all the arrows, all of them. Every possible path contributes an arrow, and you add them all together, tip to tail, and wherever you end up, that tells you the probability that the photon does that thing. And here is why the glass thickness matters. When the glass is thin, the photon can reflect off the front surface or the back surface. Those are two different paths. Each path has an arrow. If the glass is exactly the right thickness, the two arrows point in opposite directions. They cancel. Zero reflection. If the glass is a different thickness, the arrows point in slightly different directions. They add up to something, 4% reflection, or 8%. The exact amount depends on how the arrows line up, and that depends on the glass thickness. You see, this is not just a teaching metaphor. This is not Feynman trying to make things simple for people who do not know math. This is actually how the calculation works. You really do add up amplitudes for every possible path. And when you do this, when you follow this procedure exactly, you get predictions that match experiments to 12 decimal places. 12 decimal places. Think about that. Feynman used to say this is like measuring the distance from Los Angeles to New York and getting it right to the width of a human hair. No other theory in the history of science achieves this kind of precision. Not Newton's gravity, not Einstein's relativity. Nothing comes close to the accuracy of quantum electrodynamics. But here is where it gets really strange. Remember, I said the photon takes every possible path. Let me tell you what that means. You shine light at a mirror. The light bounces off. You see your reflection. Simple, right? Classical physics says the light takes the shortest path. It goes from the source, hits the mirror at just the right spot, and comes to your eye. The angle of incidence equals the angle of reflection. You learned this in school. But quantum electrodynamics says something different. It says the photon does not just hit that one spot on the mirror, it hits every spot on the mirror. It bounces off the top edge, it bounces off the bottom edge. It bounces off your neighbor's mirror across the street. It takes paths that curve through space like crazy spirals. Every path you can draw, the photon takes it. All of them, simultaneously. Now, you are probably wondering, if the photon takes every path, why do we only see the straight line reflection? Why does light appear to travel in straight lines? Here is where the math becomes beautiful. For most of the crazy paths, the little arrows spin around wildly. The path that goes way up and then way down has an arrow pointing one direction. The path right next to it has an arrow pointing almost the opposite direction. When you add up all these crazy paths, the arrows cancel. They point every which way and they add up to nearly nothing. But near the classical straight line path, something different happens. The paths are all very similar. The arrows all point roughly the same direction. When you add them up, they reinforce. They all contribute to the same result. That is why light appears to travel in straight lines. Not because photons know to do this, not because there is some law forcing them to take the shortest path, but because the quantum math, when you add up all the paths, produces the classical straight line path as the only one that survives the sum. And you know what? This is not speculation. In 1948, a physicist named Richard Feynman worked this out completely. He won the Nobel Prize for this in 1965, sharing it with Schwinger and Tomonaga. The Nobel Committee said this was one of the most important achievements in 20th century physics. And they were right. Let me tell you about one of the strangest predictions of this theory. Virtual particles. Now, you have probably heard this term. People say empty space is not really empty. It is full of virtual particles popping in and out of existence. That sounds like poetry, like a metaphor. But it is not. It is a real prediction of quantum electrodynamics, and we have measured it. Here is what the theory says. An electron sitting in space is surrounded by a cloud of virtual photons. These photons do not really exist in the sense that you can detect them directly, but they affect the electron. They change its properties slightly. The electron's magnetic moment, the strength of its tiny magnetic field, is not quite what you would calculate if you ignored these virtual photons. The difference is small, very small, but it is measurable. And here is the remarkable thing. Physicists have measured the magnetic moment of the electron to 14 decimal places. 14. And they have calculated it using quantum electrodynamics to the same precision. The two numbers agree completely. The measured value is 1.0015965218.073. The calculated value is 1.0015965218.085. The difference is in the 13th decimal place. Let me put this in perspective. This is like predicting the distance from New York to Los Angeles to within the thickness of a human hair. No, better than that. This is like predicting it to within the thickness of a virus. This level of agreement between theory and experiment has never been achieved in any other field of science, not even close. Now, you might ask, how is this possible? How can a theory that talks about photons taking every possible path, including paths that go backward in time, how can such a theory be this accurate? And the answer is nobody knows. Well, we know how to do the math. The math works. But what it means, what is really happening, that is not clear. Feynman himself said, if you think you understand quantum mechanics, you do not understand quantum mechanics. But there's something even stranger, something that bothered physicists for years until they figured out how to think about it properly. You see, when you start calculating things in quantum electrodynamics, you run into infinities. You try to calculate the mass of an electron, and the answer comes out infinite. You try to calculate its charge, and that comes out infinite too. For a while, this seemed like a disaster. The theory gives infinite answers. How can that be right? But then physicists realized something. The mass and charge you calculate are not the ones you measure. What you measure in an experiment is the mass and charge of an electron surrounded by its cloud of virtual particles. The bare mass and charge, the ones without the virtual particle cloud, those are not measurable. They might as well be infinite. It does not matter. What matters is the dressed mass and charge, the ones you actually see, and those are finite. This process, this idea of separating the measurable quantities from the unmeasurable infinities, is called renormalization. And it works. It works beautifully. You take the infinite answers, you subtract them in just the right way, and you are left with finite predictions that match experiment to 12 or 14 decimal places. Freeman Dyson, very brilliant fellow, proved in 1949 that this procedure is mathematically consistent. The theory works. Now, here is something practical, something you use every day without knowing it: the GPS system on your phone. It uses satellites orbiting the Earth, and those satellites have atomic clocks on them. The clocks need to be incredibly precise because they are measuring the time it takes for radio signals to travel from the satellite to your phone, and any tiny error in the clock translates to a big error in your position. But there is a problem. The clocks on the satellites tick at a different rate than clocks on the ground. This is because of relativity, both special relativity, because the satellites are moving fast, and general relativity, because they are higher up in the Earth's gravitational field. If you do not correct for these effects, the GPS system would be off by several kilometers after just one day. And how do you calculate these corrections? You use quantum field theory, the same mathematical framework that gives you quantum electrodynamics. The same framework that talks about photons taking every path and virtual particles popping in and out of existence. That framework, as strange as it is what makes your GPS work. Every time you use your phone to navigate somewhere, you are using quantum mechanics. You are using Feynman's little arrows. Let me tell you one more thing, something that shows just how deep this theory goes. In quantum electrodynamics, there is a number called the fine structure constant. It is a pure number, no units. Its value is approximately 1 divided by 137. This number determines the strength of the electromagnetic force. It tells you how strongly charged particles interact with each other. Now, here is the thing. Nobody knows why the fine structure constant has this particular value. We can measure it, we can use it in calculations, but we cannot derive it from anything more fundamental. Feynman called this one of the greatest mysteries in physics. He said all good theoretical physicists put this number up on their wall and worry about it. The value of this constant determines everything about chemistry, about how atoms bond together, about why matter has the properties it does. If it were slightly different, atoms would not be stable, stars would not shine, life would not exist. And yet we have no idea why it has the value it does. It is just a number we measure, a number that falls out of the structure of the universe, and we do not know where it comes from. But here is what we do know. We know that quantum electrodynamics, this theory that Feynman and Schwinger and Tomonaga developed in the 1940s, is the most accurate theory in the history of science. We know that it describes how light and matter interact with a precision that is almost absurd. We know that every time you look in a mirror, every time you see a reflection, what you are seeing is the sum of every possible path a photon could take. We know that empty space is full of virtual particles, and that these particles have real, measurable effects. And we know that light is not a wave. It is not a particle. It is not a wave-particle duality. It is something else, something described by quantum field theory, something that takes every possible path through space, something that cannot be visualized in the way we visualize everyday objects. Feynman said this explicitly. He said, "Do not try to picture what is really happening. The universe is not obligated to make sense to your visual cortex. But even though we cannot visualize it, we can calculate it. We can predict what light will do in any situation. We can measure those predictions to 14 decimal places, and they are correct every time. The theory works. That is what matters. That is science." You see, there is something profound here, something about the nature of knowledge. We have a theory that works better than any other theory in history. It makes predictions of stunning accuracy. It explains phenomena that classical physics could not touch. And yet, at its heart, it describes a reality that is nothing like what we experience in everyday life. Photons taking every path, virtual particles appearing and disappearing, probability amplitudes represented as spinning arrows. This is not how reality appears to us, but this is how reality works. And Feynman gave us the tools to calculate exactly what it does, even if we cannot visualize what it is. He gave us a way to handle infinities, to add up infinite numbers of paths, to predict the future with breathtaking precision. He gave us quantum electrodynamics, the jewel of physics, the theory that describes light and matter and how they dance together. And here we are, made of atoms that obey these laws, trying to understand how it all works, using brains built from quantum mechanics to understand quantum mechanics. That is beautiful, I think. That is what science is. Not comfortable stories, not easy visualizations, but accurate predictions, deep understanding, the truth, whatever it looks like. When Feynman gave his lectures on quantum electrodynamics in 1979, lectures that became a book, he ended by saying something very simple. He said, "That is how light works. That is what we know. And if you do not like it, too bad. That is what nature does. We did not make the rules. We just discovered them. And you know what? That is exactly right. The universe does not care what we think makes sense. It does not care what we find intuitive. It just is. And our job, the job of physics, is to figure out what it is doing, to measure it, to calculate it, to understand it as deeply as we can." Quantum electrodynamics is that understanding. It is the most accurate theory we have. It describes how light behaves when it hits glass, when it bounces off mirrors, when it interacts with electrons. It explains why some light reflects and some goes through, and why the amount depends on the thickness of the glass. It explains the strange patterns that classical physics could not touch. And all of it, all of this stunning accuracy, comes from one simple idea. A photon takes every possible path. You add up the probability amplitudes, and somehow, against all odds, this gives you the right answer. Every time. To 12 decimal places, to 14 decimal places, to whatever precision you can measure. That is quantum electrodynamics. That is the theory of light and matter. That is what won Feynman the Nobel Prize. And that is how we know that light is not what you see. It is something far stranger, far more beautiful, and far more precise than anything we could have imagined.